Okay, please take your seats. We're about to start again after lunch. So we're opening up the next session here. We have a bunch of very interesting speakers, and the first one is John Stuart Reid, and he will be introduced by Vladimir Voykov, actually.
Thank you very much. I would like just to introduce John Reid, whom I met only 2 years ago at some seminar, small conference in London. And he impressed his presentation and later on this demonstration impressed me very deeply. Because I understood that we usually separate science and art. Art is something very specific and science is also very specific. And here, for me, at least personally, it was elite science and elite art indivisible. And I hope very much he had presentation last year at this our conference, and I hope very much that you'll get tremendous pleasure, not only new knowledge, but also the aesthetic pleasure from this lecture. Thank you very much.
Thank you so much. Good afternoon, everyone. Just like to begin by saying what a marvelous conference, so inspirational, and I thank all of you that have presented so far because it's joined a lot of dots for me. And I'd like to begin by thanking Professor Pollack for his kind invitation, and also to thank his whole team, because it's so beautifully organized, this conference. And I was here 2 years ago with Annalise, and again, beautifully organized. So thanks very much to the team, and also to the AV guys who are also doing a wonderful job. So please, can we put our hands together? So, welcome to my toy shop. I say that because every day when I'm working in the lab, I actually feel, sometimes anyway, not always, but I sometimes feel like a child playing with toys, excepting, of course, that in my adult self, there's always a purpose to the playing that I do. And I'd like to begin by, well, first of all, saying that you might notice that I've changed the title to Life-Giving Water Patterns. I've abbreviated it simply because, well, you'll find out in a moment or two why that title, but also just to say that I've added new material that was not mentioned in the program. So I had to have a kind of general title. And also to explain this image. Does that image not look computer generated? I think you'd all agree that it looks like it was created in some Photoshop platform or something like that, some kind of graphics platform. But in fact, that is sound made visible using the CymaScope instrument, which I'm going to introduce you to in a moment. And but before we get there, just to say, I think you can see in that image that there is three-dimensionality. It's not a flat 2D image. If you look closely on the screen here, it is very, very 3D. And but even there, I think you can see a three-dimensionality. And this is because when water is impressed, when you imprint sound onto water, you're not only structuring the surface of the water, but also significantly into the depth of the water. You're organizing all of the molecules with the sound, and that is why when the camera picks up that image, it's actually seeing some layers that are in clear focus and other layers that are further away and slightly out of focus, and that's the reason that you're seeing that effect. Also, just to mention that this is the image of a male voice made visible, and you'll notice that it has seven-fold structure. And this is a strange thing, that this male voice, he was chanting when we captured this image, almost every time that I image whether a male or a female that are spiritually oriented, it's sevenfold. Now, I can't explain that, but I just thought I'd mention it because it is interesting. Something to think about. So, this is my little menu. We're going to begin with a water memory experiment, a nice, interesting topic for the day. And then we're going to go on to kind of the main part of the presentation, which is mentioned in the program, CymaScopic Planckian distribution equation analysis method, a bit of a mouthful, but it's concerning differentiating between the sounds that cancer cells make and healthy cells make. So it's a very interesting and hopefully will become a powerful method in the future. And then finally, it's a little bit of a, I'm kind of laughing inwardly at this last one, abiogenesis, ocean seeding by comets, because I'm hearing the voice of my parents who are saying to me, you sometimes tread where angels fear to tread. And, you know, perhaps today will be one of those occasions. I'm not really sure. I'll leave you to decide when we get to that point in the presentation. Anyway, so to begin. Before we get to the water memory experiment, let me just very quickly introduce you to the CymaScope instrument, which I developed over a number of years. And I think you can see here what looks like a petri dish. It's actually a fused quartz cuvette with a black fused quartz bottom to maximize the contrast. Into that little, we call it a visualizing cuvette, we put a small volume of water. That particular size of cuvette, we put 6.8 milliliters. And then you'll see that we have above here a light source that is firing. It's coaxial with the fused quartz cuvette, and it's basically just firing light down into the water. And then in the body of the instrument here, we have a voice coil motor which is injecting sound directly, direct coupled into the water. And what happens when you do that is that you are effectively transposing the sonic periodicities to water wavelet periodicities and simply, in effect, making the sound visible. And I know some of you will be thinking immediately, but what about the electromechanical resonances in that system? Well, what we do simply to negate those is we tune them out by feeding in a characteristic in the signal processing software, which is the inverse of the resonant characteristics of that electromechanical system. So, in other words, when we put a sound in, we get an analog or a model of that sound as a pattern. Okay, so it's now geometry, basically. One more slide before we get into the water memory experiment, and this is just to answer a question that, again, has probably immediately occurred to you. How can you image long wavelength sounds on a very small water membrane? And the reason is simply because of the compression ratio that exists between the density of air and the density of water. And that compression ratio at normal sea level and 20 degrees is approximately 829 to 1. And it's actually the reason why I think our cochleas are able to also sense very long wavelengths. And I give an example there of the lowest note on a piano, 27.5 hertz, has a wavelength of 12.37 meters, and which you can, I mean, visualizing that, that's a long way. And yet the little 30 millimeter long cochlea, if you unwind it, it's about 30 millimeters, is able to sense that long wavelength. And I believe this is the reason, and it's also certainly the reason why we are able to image very low frequency sounds. The bandwidth of the instrument goes down to 3 hertz, and it goes up to, we can push it to 5K, usually 3K, 3000, but we can, under some circumstances, go to 5K. So that's enough about the instrument. Just also to say that This here is actually a photograph, literally a photograph, taken by the camera looking down into the water with that particular frequency. Okay, so, and you can see that the distance between each of these rings here represents half a wavelength. Okay, that's enough of the technicalities. So, this is the first video that I'm going to be showing today. And I need to explain a little bit about this video before it begins, because it was simply, I did this as a precursor to a series of water memory experiments that I am planning to conduct. It's only a precursor, so please remember that. And the reason I think I'm saying that is because the method that I'm using for timing is very, well, you could say casual or informal, but, you know, reading the text there, you know, where I say that within the space of 90 seconds in real time, the time it takes for a pattern to appear on the surface of the water and indeed the subsurface shifts from circa 6 seconds to circa 3 seconds. And I'm safe in saying that if there was a man on a galloping horse doing circles in here, watching the video as it occurs, I think even he would agree, or she would agree, that, that there's a real effect here. And every time I do this experiment on this kind of informal method, I get a very similar result. So with that, I'm going to play the video now. Water memory experiment. The CymaScope's fused quartz cuvette is charged with 6.8 milliliters of medical grade water. The frequency generator is set to 9.87 Hertz. I'm going to ramp up the amplitude while simultaneously starting a timer now. That took circa 6 seconds to reach full expression. I'm going to ramp up the amplitude again now. That took circa 5 seconds to reach full expression. I'm going to ramp up the amplitude again now. That also took 5 seconds to reach full expression. I'm going to ramp up the amplitude again now. That took circa 4 seconds to reach full expression. I'm going to ramp up the amplitude again now. That also took circa 4 seconds to reach full expression. I'm going to ramp up the amplitude again now. That took circa 3 seconds to reach full expression. End of take. So if there was a man on a galloping horse, hopefully he would see that. This is a real effect. So what is going on? Well, it seems unlikely to be individual water molecules that are somehow storing that frequency information. Simply because of Brownian motion, you would think, anyway, I would think, would cancel out any effect of that nature. But perhaps if we're now talking coherent domains and millions of water molecules, well, there may be a potential mechanism there to consider and to think about. The other aspect to this, which because of some of these wonderful talks that we've heard this morning and yesterday, mentioning the infrared component, well, of water I'm talking about now, absorption spectra and so on of water, I think it's worth mentioning that every sound that is made on this earth has an electromagnetic component. And almost all of the sounds that we hear on this earth are in the electromagnetic component is in the infrared spectrum. So the sounds that I'm making now are actually generating infrared, and the infrared so generated is modulated in amplitude, you know, by the frequencies in my voice. So when we're injecting sound into the water, we're not only injecting sound, we're also injecting infrared. So that's possibly another part of the puzzle that we have to bear in mind. Another thought in this relation is Faraday wave patterns on a circular membrane can be considered representative of a 2D slice through a 3D sound bubble, because the crests of the waves are in phase with the crests of the initiating sound. So what I'm talking about now is the fact that as I'm speaking, there's a bubble of acoustic energy coming out of my mouth. Many people call that a wave. I don't call it a wave because it's a misnaming from my perspective. It's a bubble. A bubble's a bubble's a bubble. And so this bubble, if you take a cross-section through the bubble, this is what you're actually seeing in this case, and this is actually the sound of a healthy cell made visible. But now have a look at this. This is the sound of a cancer cell made visible. Now, there's a wonderful new method of analysis to be able to differentiate not only between the sounds of cancer cells and healthy cells, but also almost any aspect of science this particular tool can be used. So let me just first of all explain the tool. But before I do, let me just say that where did we get these sounds from? Well, there's a collaboration between Professor Sung-Chul Ji of Rutgers University and Birmingham University in the UK and Glasgow University in the UK. And together we are collaborating on this particular venture, and they are using Raman spectroscopy, scattered light, which they then characterize, sonify, and create a sound file, which we then put into our instrument, and then we get these various pictures, which are, by the way, they're not static pictures. These are videos. So although I'm showing you static images, they're dynamic images. And, you know, any cell has respiration. So the healthy cells are respirating, and as they're doing so, we're getting a range of these beautiful pictures coming out. And with the cancer cells, unfortunately, not so beautiful, as you might imagine. So this is a kind of summary of the Planckian distribution equation. If you'll forgive me, I'm going to read it because it's probably better that way. You might get the principle. And of course, take any slides, pictures if you wish. The PDE method can be applied to any long-tailed histogram and is sufficiently powerful to quantitatively characterize the profiles of histogram curves. To differentiate between any two cymaglyphs, this is the name we give to a sound image. The process begins by capturing CymaScopic imagery with a Blackmagic video camera, which outputs frames in RAW format. It could be any manufacturer, but we happen to be using a camera manufacturer called Blackmagic. The RAW frames are first analyzed by RAW Digger, which is proprietary software, which outputs a histogram and a .csv file. This data is then reduced to two numbers by means of the PDE algorithm, and when plotted on a Planck-Shannon plot, the graph's slope provides a correlation coefficient that can be used to compare, in this case, the sonic signatures of healthy cells versus the sonic signatures of cancer cells. Bit of a mouthful, but you get the idea, I think. And here is the actual physical setup in our lab. And here you see, this is the Blackmagic camera, well, it clearly says so. Then you have a nice macro lens firing down through the light ring receptacle, which is coaxial with, you can just see the cuvette there below. And then over here, you've got a rack full of signal processing equipment. So it's a very simple setup, but it works extremely well. And not only for this work, but also for, as we'll get to, for many other sciences. So this is really what it's all about. So we heard that Birmingham University and Glasgow University were trying to develop a method, or are trying to develop a method, to differentiate in real time between the sounds of cancer cells and the sounds of healthy cells. Why? because when a surgeon has a body open, or in this case a skull, and has the knife and is needing to remove a tumor, apparently it's not that easy to differentiate where does the tumor end and the healthy tissue begin. Never seen it myself, but I can imagine. And here you see a brain that's been opened and a tumor that has been removed, leaving, you know, a big hole. And apparently the coloration of the tissue is so similar that it's very difficult to tell. So what they are developing is this method of real-time differentiation with a feedback to the surgeon. And in this case, what they're trying to do is to use audio only. And so far, their success rate has been about 70% in trials, where students that have been challenged to differentiate between the sound files from the healthy cells and the cancer cells in real time have had that kind of success rate, about 70%. Obviously nowhere near what it needs to be. It would need to be, what, 99.99, you know, for the system to really work efficiently. However, what I would love to mention now is that the CymaScope instrument, even with absolutely tiny changes in any audio that you put into it, creates a really large change in the pattern. So, however, it would not be particularly practical to have a real, you know, physical CymaScope in an operating theater. Instead, what we're hoping we can achieve in the future is a fully software version of a CymaScope, and then all the processes that I'm just about to explain would all be done in real time. So with a delay maybe of 2 or 3 milliseconds, the surgeon would, he or she would see in her or his glasses literally a pattern. And as they move the Raman probe this way and this way, the pattern would change, and that would tell them where to cut. So here is the equation that, that Professor Sungchul Ji developed. He's developed it simply from the Blackbody radiation equation. And what he's done is he's simply generalized that equation. And in so doing, it means that when we create these raw files, these raw pictures, then the data from the .csv file can be exchanged into the equation, and basically what you end up with is being able to plot a graph, and it's the slope of the graph which in the end tells you, you know, whether it's healthy cell or cancer cell in this case. But as I mentioned earlier, you can apply the same principle to virtually any science. And here is a short list. I'm not going to read it all out, but you know, there's a list of some of the many sciences that you can apply this to, starting with astroseismology, analyzing the sound files from stars, all the way through to zoology, analyzing animal calls, and virtually every ology you can think of in between. And I've just put a few of them in there. And I should mention, oh, it's not in there anyway. I thought I'd put hematology in there. I didn't, but actually you can also put live whole blood into the CymaScope. That's for perhaps another discussion. So let's move on now to this abiogenesis concept. Sound, the trigger for life. Well, I think all of you will probably agree that it's a general consensus that life began in the oceans around hydrothermal vents. Of course, no one knows how that happened, but I'm going to be putting forward a hypothesis. I'm going to be treading where angels fear to tread here, and I'm putting forward a hypothesis, and you can decide for yourself whether you think there's any validity to it or not. So to begin with, I'm going to play the sound of a typical hydrothermal vent. I think we can make this happen. That's fine, thank you. So get the idea. It's low frequency sound mainly, but actually there's a lot of different frequencies. If you did an FFT analysis of that sound, you would find there are hundreds, probably thousands of frequencies that are present in that sound. And so here is a particular paper, by the way. You might want to look it up, Evidence for Early Life in Earth's Oldest Hydrothermal Vent Precipitates, going back 3.77 billion years, which is an astonishing figure. But anyway, it's a really interesting paper if you would like to look that up. Let's talk a little bit about these bubbles that are coming up out of the hydrothermal vent, filled with, of course, the gases that came from the mantle of the Earth. These bubbles vary in size. Some of them are microscopic. Some of them are the size of melons. Not in that picture, but I have seen hydrothermal vents creating melon-sized bubbles. But what I'm interested in is the resonant characteristics of these bubbles. And a little while ago, I was starting to think more. I've had this idea for many, many years, actually. But I started to do some reading, various papers on the subject, and that one included. And I came across this principle of Helmholtz resonance. I'm sure you all know what Helmholtz resonance is, but typically, you need, in this case, a glass sphere with a neck, and a Helmholtz resonator is effectively that. And there's a nice formula, that I'll not go into now, that you can use to calculate the resonant frequency of a glass bubble with a neck. But also, what I was reading in these papers is that we can consider any bubble to be a kind of species of Helmholtz resonator. And simply because it's a volume of trapped gas, and naturally it will have a resonant characteristic, right? So that kind of got me thinking, and thinking about microscopic bubbles that are coming up out of the hydrothermal vent. And some of the papers, by the way, that I read talk specifically about the seawater in contact with molten lava. This creates a huge range of microscopic bubbles, all different sizes of bubbles. So this is another little video I'd like to share with you now. And this is a field of sessile drops. So these are microscopic droplets of water. I borrowed Annalise's atomizer, and perfume atomizer, and had to do it several times to get something that was permissible to put under the microscope. But what I've arranged here is a means of exciting the microscopic droplets of water with sound, of course. In this particular experiment that I'm showing, I'd like you to focus on the two largest drops, this one here and this one here, bearing in mind that the whole width of this is about half the width of my little fingernail. It's about 3.5 millimeters or something. So some of these droplets, they're all microscopic, but some of them are fairly large in terms of human cells, are larger than human cells. Many of them are much smaller than human cells, actually. So there's a whole range of different droplet sizes here. So let me just, and remember, you're seeing the same energy is being given across the whole surface here. Same acoustic energy. So you see here two nice Faraday wave patterns, also known today in modern parlance as cymatic patterns, but Faraday wave patterns are the scientific term. And you see really nice patterns forming on those two large drops. All of the smaller drops are obviously receiving the same amount of power, same acoustic power, and yet they are not showing a cymatic pattern. Why? Simple resonance, obviously, because the mass of the droplet determines its resonant characteristics. Therefore, the small droplets in this case are not resonant with that particular sound that I was putting in. And here's a wonderful graphic by T.G. Layton, Professor T.G. Layton in the UK, who has a 500-page book called The Acoustic Bubble. And we have that book in our library, and there's T.G. Layton's graphic showing you all the primary modes of subsurface bubbles. But remembering that they're not always primary modes. They can be complex sounds with many different modes. Here, I'm going to move on quite quickly. You know the classic Yuri Stanley Miller experiment where he mixed various liquids and gases and so on, sparked them, and created simple amino acids and so on. But you know what I ask is, if you take a watch, for example, and you take all the parts out and you put it in a flask and you shake it, how many times would those random shakings, have to be conducted in order to create a working watch? I think you know the answer to that one. Here are some slides to show you how I got into all of this in the first place in the laboratory. Almost every day in my general work, looking at different frequencies for different reasons, different projects that I'm working with, I come across images like this that are showing what look like early life forms. I've got hundreds of them. There was just a few just to show you. But, that makes me think, okay, is there some connection between sound and life? Well, I think that very much that there is. And there's something showing the cross-section through DNA, tenfold, and there's a tenfold Faraday wave model. I was going to show you this video, but because I'm running out of time, I'm not going to. But I think some of you will know about Comet 67P. This was an audacious space mission by the European Space Agency, sent up a probe to land on the comet. Why? To see whether there were any organic compounds on the comet, because many scientists across the last 50 years or so have been saying that through spectrographic information they can see organic compounds in space through the spectrographically, and so they sent up that spacecraft, landed on the comet. Yes, organic compounds. So this whole idea of the ocean being seeded with amino acids and sugars and so on is now kind of confirmed. There's the comet. That was the video I was going to show you, but for shortage of time. So abiogenesis, the long ago switch from abiotic chemical reactions to biologically mediated reactions, oceans seeded by comets containing organic compounds. What happens when those organic compounds are in the water, or in case of minerals and things coming up through from the vents? There has to be an organizing principle. You can't have randomized creation of life. There has to be something, in my view, that organizes the matter, and sound is the organizing principle. And I was the one more video I was going to show you, but I ran out of time. So thank you so much for your time.
Thank you, John. Any questions to John? Yes.
Thank you, John. Stimulating as always. I wonder what would happen if you take the healthy cell sonificated sound pattern and project it onto in vitro cancer cells.
Onto a?
In vitro cancer cells.
Oh, okay.
Could you reverse the tumor or the cancerogenous process?
Maybe. What I do know is that this method of listening in to the sounds of cancer cells versus healthy cells, it says to me that simply through resonance, as we saw in that microscopic video there, that if you listen to the sound of a cancer cell, hugely amplify it, and then send that sound back into the cancer cell will immediately overheat. it will die. It has to, through amount of energy that it's receiving. Whereas because the sonic signature of the healthy cells that are nearby is so radically different to the sound of the healthy cell, then they may be a bit stressed, because you would have to certainly pump in a lot of acoustic energy to cause that overheating effect. But they're not going to die. They're just going to be a little bit stressed. That's my hypothesis. So I think... sorry? Sorry, I can't hear.
Vice versa? The opposite?
No, I didn't understand, sorry.
I have a question. When you looked at the atomizer droplets and applied sound,
Yeah.
it appeared that the pattern was confined pretty much to the core of the droplet, whereas the periphery of the droplet seemed to have no pattern or almost no pattern. Do you have any comment on, is there some difference in terms of the droplet, the peripheral region versus the core region, or is there another interpretation of that?
There's another interpretation. Thank you. That's a wonderful question. Actually, one of the videos I wanted to show you, which maybe another time, but it's submerged water droplets, sorry, submerged bubbles, actually under the water with a pattern around them, which, you know, goes with the hydrothermal vent concept. But to come back to your question, the reason that the pattern does not go out to the edge, it does, but the camera's not seeing it. Why? Because the light source is only from one direction. If I were to have multiple light sources around, you would see the pattern right round the whole bubble. This is simply due to the angles of reflection of light. So the fact that it's a convex surface means that only certain angles will send the light back to the camera. That's the answer to the question. And I found the same thing, by the way, with submerged air bubbles. If you photograph those with a single light source, you see the pattern only on a certain area of the bubble and not round the whole bubble. So in future experiments, I will be sending light in from the sides as well, so that I can see the whole pattern around the bubble. Yeah.
Well, thank you very much for this wonderful presentation. Since you're talking about the origin of life and an organizing principle, I will allow myself a very unscientific comment. Well, there's a very well-known book that says, in the beginning there was the Word, and perhaps that is just a metaphor.
Well, thank you for that comment. It's of course, it's not only in the Christian tradition. That same tradition is in the Vedic tradition and many other religious traditions around the world. And of course, it raises the question, how did these ancient people know that? I'm not going to go there, but you know, the fact is that there are these ancient traditions, and they all say, I mean, like the ancient Egyptian, for example, the god Ptah, he said almost the same words. And where did these ideas come from? I don't know, but it's really interesting. Thank you.
Yeah. The previous question was, what would happen if the signal from a cancer cell is transferred to a healthy cell?
I understand, yes, I understand the question. I think this is just my interpretation right now. I think the healthy cell would not appreciate that. It would be like for any of us in this room to be listening to distorted music. It would stress us. We would not be happy about listening to distorted music. We like to listen to harmonic music, you know, that's beautifully organized and everything's harmonically related and no distortion, no square waves or whatever. You could see from that picture of the cancer cell, you know, made visible, that it's distorted, it's ugly, basically, yeah. Subjectively ugly. So I think the healthy cell would not appreciate it. I don't think it would die, but I think it would be stressed. It might go into the G0 phase and wait for, you know, it would protect itself and wait for the sound to go away. And when the sound goes away, it would move into G1 and start to replicate again, hopefully.
Understood. But then I was thinking about the medical doctor that will listen to this sound.
Oh, the medical doctors?
Yeah, operating the... Oh. Yeah, that's another question.
Well, again, I think that provided the level is moderate, you know, that you're listening to, we as humans can listen to any distorted sound, providing the level is moderate. But if it's too high, it will actually cause damage. And the same principle applies to all forms of energy, doesn't it? We can lie in the sunshine for 20 minutes, maybe. Well, in the UK you can, maybe not here, I don't know. But you know, if you lie in the sun for 20 minutes, it gives you vitamin D and all sorts of other wonderful things happen in your body. If you lie in it too long, you get sunburned. It's the same with all forms of energy. Moderate is not going to cause any problems, I think.
Thank you. It's me now. Is it on? I want just to know, Royal Raymond Drive, he made a ray beam machine already in the 30s, and he could cure cancer with that, but he was actually killed. So it's an old area already, and has been a lot of scientists in this. So just to have this in mind, that there have been machines that could kill the cancer from sound. Another thing I would say, I work with the sound daily with my voice, and I would like to ask you, do you think that we, by making like this sound, like for example, close to the earth, the sound you showed us, could stimulate ourselves? Because if we can do it ourselves, it's very simple.
The voice is a very healing instrument. Annalise and I have just returned from Bratislava, heard a wonderful lecture by Dr. Professor Sergei Petukov, who mentioned that the ratio between the second and third harmonics, not specifically of the voice, he was talking about strings, you know, on pianos or harps or whatever, any other kind of musical instrument. The ratio between the second and third is the golden ratio. And of course the golden ratio is embedded throughout all of life. So therefore, he also, other information he gave relating to this ratio in DNA. So in a sense, when we sing, we are singing directly to our DNA, and it's a beautiful harmonious sound that we make. So yes, I think it would be very healing indeed.
Okay, good. So we thank John again.
Thank you very much. Thank you.
Thank you so much.